Hello everyone and welcome to a new discussion under this groundwater engineering course, and this discussion is basically continuation of our groundwater exploration, and this is part 16. So far we have been discussing about geological explorations, then geophysics, then well logging, and now we will be in this particular section we would be more focusing on which types of wells should be developed, and also same time we would like to also discuss about the exploration for artificial recharge sites, because ultimately that is also very important from groundwater engineering point of view. And nowadays, especially in hard rock terrain in India, it is very much required, where we are having a negative budgeting or lowering water table in many states of India. So efforts are required for such artificial recharge sites, identification and development of such artificial recharge site. So what type of wells we should be developing? So types of well based on our exploration which we have done so far, as I have said, geological, geophysical, well logging and other things. So whatever the information which has been gathered so far, surface and subsurface, that will be utilizing into the selection of types of wells. So as we know that the subsurface hydrogeological conditions such as degree of consolidation of formations, thickness, depth, texture of materials, nature of salinity stratification, that will dictate our the type of groundwater surface structure suited to obtain satisfactory yield on a sustainable basis. That's there we can develop a well, but if it does not provide water for round the year and for whatever the desired quantity, then it is not a successful operation. So all these things are kept in mind, and through these subsurface hydrological investigations we get lot of such information. Now common types of structures which are feasible under different conditions. So two different major conditions are that either we are having alluvials or soft rocks, or in another conditions are very hard rock and like maybe granitic terrain, metamorphic terrain and so on. So we would be comparing these things between the hydrogeological conditions and what type of suitable groundwater structures are possible in those conditions. So the first one is when we are having shallow aquifer comprising weathered and fractured zone underlain by unfractured rock, and in a typical granitic terrain this situation we have been also discussing this situation, that you generally get the water at a shallow depth, and we say in unconfined aquifer conditions, and so the water is available only in weathered and fractured part of the rock, but underlying rocks are unfractured or consolidated rocks. There is no weathering or fracturing deep inside. So for such a type of terrains where we are having hydrogeological conditions, then large diameter wells with tunnel in the horizontal direction, galleries added, and angular or horizontal bores to intersect water bearing fractures. Because here the main carrier of water, or I would say secondary permeability which is being provided, is only by the fractures which are present in a rock and within this weathered zone. So if it is possible, then horizontal tunnel, gallery, edit and angular or horizontal bores will be required to be done in a large diameter well, so that the more water from the surrounding can also enter into the well, and which then can be pumped out and used. Similarly, in case of we are having a weathered but at the same time claying material of caving type, means they are making some cavities inside, and then above with deep water bearing fractures, or these things are present, then the best solution in such things, the suitable groundwater structures can be that we are having a blank casing from the top to hold the weathered zone, so that the well does not collapse inside, from caving an open hole at the bottom. So in the bottom part we will have a opening or a screening depending on type of formations. So that will only those screen or space or slits will allow the water to go into the well and which can be pumped out. But the top part will have completely blank casing and no screening, nothing. Why? Because this part is having caving and other thing. What I am trying to convey here, that different hydrogeological conditions, these are the conditions and appropriate solutions for individual well has to be found out. And this is what it is done, that we are considering only certain type of scenarios, but there can be all kinds of scenarios which cannot be narrated or cannot be discussed in a short video. But in real conditions, as per the lithologs which is available, based on that, or if we are having geophysical investigations or well logging data, then accordingly the whether which part of the well should have a blank casing, which part of the well should have a screen, which part of the well have a bottom or a bottom hole at or hole open hole at the bottom, and so on. If we go for granular coarse textured weathered zone of consolidated rock from aquifer, which if aquifers are in a granular coarse textured weathered zone of consolidated rock, then these are the good for artificial or a natural gravel packed well. And because you are having coarse grain and this is weathered or coarse textured weathered, and therefore for suitable groundwater structure can be artificial or natural gravel pack might be required to certain depth, so that the well remain productive for very long time. Now, common types of structures which are feasible under different conditions, we continue this discussion, that when we are having stratified thin permeable horizons which are underlain by well defined impervious layers on hill slopes, such as in the volcanic rocks, if one condition is there, then tunnel contouring the surface of permeable layer, and that will allow water to become available in a well. If we are having unconsolidated coarse texture material from shallow aquifers, in some case it is a very good that we are having unconsolidated material, we are having coarse texture, that means porosity and permeability, and that too in a shallow aquifer condition is going to be very good. So, for that purpose we can go for a shallow large diameter dug or tube well, a collector well, that well with the lateral perforated tubes. So, sometimes this is also one of the solutions in such kind of hydrogeological conditions, that we are having a well which is called collector well, and which will collect the water, and then from some other place you can take out that water. So, these are the thing. Again, if I mention that nowadays this is a large diameter dug well, and basically in a hard rock terrain, when we are having shallow groundwater conditions, people can go for large diameter dug wells, but it is becoming uncommon nowadays. Most of the people are going through for the tube well or a bore well and then installing a pump on there. So, such in unconsolidated coarse textured material, when we are having and forming a shallow aquifers, then the shallow large diameter dug well, tube well or collector well very effective in capturing subsurface flow below stream beds. So, in certain conditions, when also you are having a stream or some riverlets or rivers are there, then for that these are also very good. Collector wells, if you recall, once I brought a few photos of these collector wells for water supply to the Devprayag city, and those collector wells were just capturing subsurface flow stream beds, and inside a river in the bend it was located, and those are nothing but the collector well, or they are also called the riverbed wells. So, the wells they can collect the water, and when water comes into the well, that is coming through the sediment, so automatically it get filtered more or less by natural processes, and then you take out that water or pump out that water. So, such kind of things, and that is a large diameter well, the example which I shown of Devprayag. So, there are others like in other hydrological conditions, only some of them we are discussing. Like when we are having phreatic aquifer and with the thin lengths of fresh water floating over saline water. Now, thin lengths of fresh water floating over saline water, that might be a situation in certain cases. Then the suitable groundwater structure can be, we can have trenches, tunnels or wells designed to skim off upper part of the fresh water. Not interested in saline water. So, the way it will be done, that we only extract the upper part of the fresh water to prevent saline water upcoming, natural or artificial gravel pack wells for horizontal or low angle bores. So, this saline water situation are faced in coastal areas many times. So, there in those situations this kind of solutions are developed or provided, or this kind of structures are developed. So, that we will only exploit the top part which is containing the fresh water. Rest of these things will be sealed or will not allow that to flow into the well. Now, other conditions can be like deep unconsolidated granular material is forming an aquifer. Then these are again natural or artificial gravel pack, a possibility there, or a suitable groundwater structure. When you are having thin caving type aquifer material underlying non-caving aquiclude like stiff clay. Clay works as aquiclude as we know. So, cavity type well, that is the cased down to the aquiclude with blank pipe. So, only the where the where the water can enter, only that part is left open or through slits or screen, rest part is completely cased down to the base of aquiclude, and in that way a structure can be developed. So, many times the solutions are what we are seeing so far, the solutions are coming about to what length we should have a blank pipe, for what length we should not have a blank pipe or a screen pipe, and what is the scenario at the bottom, whether bottom part should be left open or it should be kept, so no water can enter from there. It will all depend, these measures will only come when we are having sufficient information about subsurface conditions. And we have seen in our previous discussion in this groundwater exploration up to this, that for that you need geophysical investigations, and that too through well logging, and then only appropriate design of these casing and screens can be done very successfully, and then well will remain productive for very long time. If we are having a near surface aquifers, again means shallow aquifers in vertical or steeply dipping folded strata, this can be a scenario in many parts of India too, or dike compartments in mountain slopes. If it is there, then horizontal or low angle bores or perforated tubes, that will also help. So, if beds are dipping, we would like to exploit, then we can have a low angle boring as well. And such boring are being done now. There are machines are available, drill machines are there, and many of us might have seen that when these cables are being put alongside the road by these mobile companies, they are doing the boring which is heavy low angle or inclined boring initially, and then they go for horizontal boring also. So, it is possible, but their boring is not very deep, only 1 or 2 meters, but that technology exists, machinery exists, and as per the requirements of our water or as per the hydrogeological conditions, such measures can also be done, that horizontal or low angle bores can also be developed with perforative tube or not perforated tube, and that will allow the water, because the condition here is that we are having a near surface aquifer or in a folded strata. Now, many examples many of these earlier hydrogeological conditions and suitable groundwater structures which we have done the comparison kind of thing, and now we would see that what are the situations here in this schematic, that if I start from left, that there is a bore well and this is in a weathered rock, might be granite or other things, and then it is going in some sedimentary rocks or other parts. So, only the casing is being provided here in the weathered part, and then you get the water quite easily. And this the dotted section is the screen part of that well. So, one example, when we are having such kind, the top part is weathered, and here the water table is also shown here, as you can see that water table with the dashed line almost horizontal or almost following the topography. Now, from groundwater recharge point of view also, like galleries are there, we have mentioned galleries. So, this kind of wells can also be developed, and these wells will exploit this part which is having some inclined features, and see this opening here, and you get the water in this gallery also. There can be a large diameter bore well like dug well here with bores, and some inclined which are exploiting this horizon, and also going below, and you are getting that water in this well. Similarly, we are having a collector well as just discussed here, where we are having a nearby a river. Example I have given already of Devprayag, near Devprayag for water supply. And what they have done some horizontal bore wells also at the bottom. So, the river water, and this is obviously the aquifer. So, in order to have the maximum exposure to the aquifer, which will supply water to the well, becomes available, and therefore, these are called collector wells. The yield from these such wells would be very high, because we are covering not only along the well wall, but we are covering large area through these horizontal wells or edit also. When we are having a situation where we are having a river which is recharging the groundwater regime, and aquifers are there. Typical tube wells are like this, that initially it might be a little large diameter, and then you go for small diameter. Some part is screened, some part is because it is going in hard rock. So, even if blank pipe is put, no problem. And then you are having a fresh water versus saline water issue here at that interface. So, only the top part is exploited, or this part may be sealed here or cased here, and only this part is exploited of this aquifer, and this part rest is completely with having no screen at all. And this well, in such condition, this well can also be successful. Now, cavity well, when we are having cavity scenario like here, a cavity scenario is there. So, this is hard clay or aquiclude. So, no use of going deeper. So, only up to this has gone, and then having a cavity that will supply water, and this kind of wells, though they are shallow wells, but will provide the can provide some amount of water, because in this schematic it is almost end of this aquifer. Now, the trenches options are also there in a hilly slopes kind of situation. So, the slope a kind of thing is shown here. So, you may have this coastal region or some other problem. So, here what is being done through the trenches, only the top part of this is being exploited, and here you are having fresh water, saline water interface here. So, you are having here fresh water, you are having saline water. So, only this by this only the top part is being exploited, which is having which is containing fresh water. So, these are the various types, not this is not exhaustive thing, these are only a major one which we can discuss. But as I have said, each and every site is unique, not only geologically, hydrogeologically it is unique on surface as well as on subsurface. So, therefore, accordingly the type of well should be chosen. So, only some types of wells, groundwater structures which are feasible under different hydrological conditions are have been discussed here. Now, when we are looking for very important work in groundwater engineering nowadays, and especially in hard rock terrain, for artificial recharge sites, we are now not exploiting water, but we are trying to recharge our aquifers through whatever the water is available. So, search for suitable sites for artificial recharge involves identifying suitable locations underlain by material having high permeability and where available pressure heads are adequate for intake of well. So, where we can do the artificial recharge, like here you see that injection well is there, which is nothing but a for artificial recharge site. So, from here the water is allowed and it goes there and it is creating, this is aquiclude. So, it is not allowing water to come up, but here unfortunately here in this example we are having an interface. So, only top part will have fresh water, rest is having saline water, and in between you can have also aquifer conditions, confined aquifer conditions, which is continuing here. So, this is also having confined. So, when you pump inject the water through this, then it will recharge our aquifers, maybe even confined aquifers. But in order to develop such sites, earlier explorations about a well location would be the same as for wells for pumping out the water, because you need to have complete all those informations about subsurface conditions. Then only such sites can be developed for artificial recharge. So, entire geophysical or well logging things would be done. Also on the surface hydrogeological conditions would be investigated, and once things are sure at what should be the depth of this well which would do the recharging of our aquifer. Preferably if it is there through these wells, then we can go for this confined aquifer conditions. If it is in hard rock terrain where only the top part is weathered and fractured, then probably through surface structures we can go for artificial recharge rather than going through these injection wells, because again this is going to be an expensive solution. First a lot of investigation is required and then allowing water to go. Similarly here in this we are having a source well, injection well, spreading basins, and all kinds of scenarios are possible depending on what hydrogeological conditions and subsurface geology is there. And the most cheapest and easiest way of doing artificial recharge in a unconfined aquifer conditions is using locating sites which are only on surface. So, small check dams, trenches and other things will delay the surface runoff, and then your unconfined aquifers can be recharged. Let me take an example from weathered, fractured, unconfined granitic terrain or any such terrain where only top part of few meters, maybe 5-6 meters is you are having water and rest you do not have because you are having consolidated rocks. So, these unconfined aquifers can be easily recharged without having any injection well or any kind of arrangement, just through the surface structures. But the storage capacity of such unconfined aquifers is not much. So, during the monsoon time you would have a full recharge of such unconfined aquifers, but after few months you may not have water in those wells. But does not matter, if we are having many such surface structures for artificial recharge, that would really help. And the main point here is to somehow delay the surface runoff in such kind of terrains and directly recharge the groundwater regime. Even if you are having confined aquifer conditions and there are some places which you have already identified from where the aquifer is getting recharged, then those are the places again surface structures can be created as shown here also, that the surface structure this ditch or basins can be created through which the groundwater will be recharged like this. So, your aquifer which is here can be confined aquifer can be recharged. So, it is not that we can using surface artificial recharge structures we will be recharging only unconfined aquifers, but we can also recharge confined aquifers, but for that purpose we need to know from where that confined aquifer is getting recharged. The site has been identified, then things becomes much easier to recharge the groundwater regime. See, this is not a finite resource. Groundwater is not a finite resource. As I have also discussed earlier, I will repeat that very briefly, that in last 120 years, the data of India of total volume of rain which is falling over India remained almost same. So, when input is same, but the problem has come because our requirements has increased because of population and growth of industries and other things. So, we need more recharging of groundwater regimes because the geology or hydrogeological is a geology or subsurface geology we cannot change. So, what best we can do to create more artificial recharge sites and basically initially on the surface, which is much easier and cost effective, identify for confined aquifer conditions, identify those areas from where these confined aquifers are getting recharged, and through that we can still have lot of storage in our surface as a groundwater. If such efforts are made, then for some time we will not have a problem of groundwater supply. Now, two examples earlier have come. One is from Gujarat, where more than 60,000 groundwater recharge structures have been developed. And earlier there used to be only one state where water table has risen, means it is not as deep as used to be before these structures. And recently in this list or not this list, now it has become list that after Gujarat, now Telangana has also done extensive work on artificial recharge, and there at some places the water table has risen by 2 meters, which is a very significant development. That means what it is showing, that artificial recharge can be done. Sufficient amount of rain water which goes roughly 96-97% of water goes as a surface runoff. So, if by some means, by such structures on surface, if can be developed, or by these wells, injection wells, if these can be developed, then we can recharge our groundwater regimes, aquifers, and get the water for long time. But as I have said, the site evaluation should take place all the time into consideration the quality of source of water. This is also important. What kind of water you are inserting, whether if it is a rainwater, then it is okay, but if it is water which is polluted, has come some contaminant, then it is not good, because by any means our groundwater should not get polluted. So, this while doing such exercises or development on surface or in subsurface conditions, the quality of source water should be maintained, so that our groundwater regimes or groundwater remains safe. So, for that subsurface hydrological condition determination is required in a large measures to design these recharge facilities, groundwater recharge facilities, and favorable sites for recharge by spreading water, that means on the surface. Overland are found in alluvial fens along Piedmont zones. So, depending on hydrogeological conditions and subsurface geology, appropriate measures, whether we should go for surface groundwater recharge structures or subsurface, that will depend. So, in case of alluvial fens, spreading water, allowing water to remain for some time on the surface, it will recharge the groundwater regime, because that is the alluvial part. And in along stream beds and abundant channels in floodplain, that is another very good area, because abundant channels are nothing but the alluvial. And there if water is held up for some time, it is definitely going to recharge the groundwater regime. You might be having sand dunes, but generally where sand dunes are there, less rain is there. So, those areas cannot be, though areas are good from groundwater recharge point of view, but water is not available. So, that option is not very much open, but glacial outwashes, eskers, cames, moraines crust, and wherever shallow permeable vadose zones are found. So, this is last part is important, wherever shallow permeable vadose zones are found, and these are the best locations for groundwater sites. for groundwater recharge sites. So, these becomes a favorable sites for groundwater recharge. Now, spatial variations in groundwater recharge rates, it depends on the basin, how what is this basin wide, like basin wide mean is 17,960 millimeter per year, means from 17 millimeter to 960 millimeter. So, were estimated in 22 major river basins across India, and so we know that there spatial variations exist in groundwater recharge rate. We know very well. Why? Because lithology is different, rocks are different all over places. So, therefore, the range of this groundwater recharge varies very extremely, means starting from 17 millimeter to 960 millimeter per year. So, anyway, wherever it is possible, possible means say if the hydrogeological conditions are allowing one and sufficient rain is there, we should recharge our groundwater regime. So, this is from that publication which I have just mentioned by Bhanja et al. 2019 in the hydrological earth system science, and from there see these are the positive and negative trends of groundwater recharge between 1996 to 2015. So, large areas are coming under red color, and unfortunately this northern part of India or Indo-Gangetic plain is showing more depletion of groundwater table than western India or in the central India or hard rock terrain, where more blue colors are there. So, only there are only few places where we are having this kind of situation, the +1, but otherwise we are having -1. So, this is again millimeter per year. So, basin boundaries are here also shown here, that Indo-Gangetic or Indo-Yamuna boundary is there, or Ganga basin in short, Narmada basin is also shown, and other Kaveri and other basins are also shown. And the blank areas what we are having no data, or these are the also hilly areas in many cases. So, for which such kind of data is not available, and probably such kind of efforts are also not being made, though we are having more rain in these areas. So, in future we have to also think and to recharge groundwater regime in hilly regions also, and collect the data so that we get all detailed information. So, if I look as basin wide annual mean recharge rates, that is millimeter per year and average. So, this is the average, and all those 22 here. So, like Ganga basin, if I take Ganga basin here, a number of wells 1048, and this recharge rate per year is 143 to 264, and that average rainfall is 979. Number of wells where it has been observed, it does not mean that number of wells in an entire Indo-Gangetic plain, that would be too large number, but here the wells which have been considered. So, if we see here that the rainfall, if it is 900 in Indian conditions, not bad, and of course, this recharge rate is not all, it is among the highest one after only the Sabarmati basin, where we are having the recharge rate of 142, 532. Otherwise, in most of the cases rate is quite low, and the rate is as low as like here we are seeing in case of this 17 to 95 in the Pennar or Krishna and Pennar basin in India in hard rock terrain. So, normally generally in hard rock terrain the recharge rate is going to be less, as we can see in case of examples from Ganga basin as well as from Krishna and Pennar basin, that here see the values are so different recharge rates. However, if you compare just rainfall, then rainfall is not having that much difference, as huge difference in case of. So, even looking this table, we know where exactly, if we put recharge structures today, then where we will get the quick recharge of or efficient recharge of our groundwater regime. So, if we create a sort of efforts in all these places, see the rainfall, the minimum rainfall here, I think it is shown only 512 millimeter per year, and this is in Luni Basin in Rajasthan, of course, and Kutch and Saurashtra including Luni Basin. So, this is in, of course, Gujarat and there. See, the recharge rate is not bad, but the rainfall is less, does not matter. Even with 512 millimeter per year annual average rainfall, still we can recharge the groundwater regime, and it has been done in case of Gujarat. So, this is whatever is the water is available through precipitation or through rainfall during monsoon, maximum amount of water, if it can be put in subsurface to groundwater recharge regime or to groundwater recharge or aquifers, it would be always beneficial. So, whether we are having a Indo-Gangetic plain where we have seen that large area is showing red area, where the depletion is happening. If you recall the GRACE experiment or GRACE data and that discussion, in which also the large depletion of groundwater table was shown for Indo-Gangetic plain, and here rain is sufficient, relatively it is sufficient. The recharge rate is quite high. So, what is required? Just we need to have groundwater recharge structures, and these red areas, large red areas will become blue, and our groundwater. See, even in Indo-Gangetic plain, if we cannot do it, then there is no, hard rock terrains are difficult, but still it is being done and quite successfully. So, Telangana example is also from hard rock terrain, Kutch and Saurashtra example of more or less of hard rock terrain with less rain, but still recharge is possible. So, the solution is there, very good solutions are there. If it is not possible to go for subsurface geophysical investigations of well logging, does not matter, even the surface structures can solve lot of problems in all these basins of India. Wherever it is possible, one should go for artificial recharge structures. So, here this map is from CGWB map which is of 2012. So, here it is showing aquifer types, transmissibility, transmissibility and horizontal hydraulic conductivity values. So, hydraulic conductivity values are shown meter per day, square meter per day the transmissivity. Transmissivity and horizontal conductivity values are obtained from this CGWB, and groundwater resource estimations methodology are obtained from this publication, that is IGV basin aquifers in here. So, what we are seeing that hydraulic conductivity shown here against different basins, and here instead of having basin boundaries are also shown like Ganga basin and Narmada basin and others, but along with their aquifer types in sense of what kind of lithology is present, what kind of rocks are there. So, they say like Indo-Gangetic plain, Ganga basin is having unconsolidated sedimentary rocks, or here we are in the crystalline fractured crystalline rocks. A large part of central India and South India is having that. So, where if you compare these two values, transmissibility and hydraulic conductivity, you say square meter per day is quite little as compared to in Ganga basin. And whereas in case of similarly in case if we look the hydraulic conductivity, then it is very high again relatively, and in case of fractured crystalline rock it is less. But more what I am trying to say repeatedly, efforts are required at all places, because our requirements of groundwater has increased many folds, exponentially it has increased, almost the same way as the population and industrial development. So, therefore, whatever the understanding about all these parameters which directly influence our ground recharges, about the knowledge which will help us to find out the best suitable sites for groundwater recharge. But whatever the conditions, one should always go for these kind of solutions, so that groundwater regimes can be recharged. Now, spreading method of recharge, one example we have seen, Vadose zones should be free of restricting layers that may impede percolation of water and built up of purged groundwater bodies. So, if it is that is the situation, then it is restricted, should not be, it should be free from the restricting layers, otherwise it will impede the percolation. So that kind of information is, minimum information is required. If the this permeable horizon is covered with fine textured material of poor permeability, as in back swamps, the scope of recharge either by excavating of low permeability layer or through wells in permeable bedose zone or aquifer to be recharged has to be explored. So, on top, if it is not possible, then at certain depth, if we are getting relatively coarse grained material or permeable horizons, then a well should be there, recharge well should be there, it should go at that level and recharge the groundwater regime. Deep confined aquifers are recharged by injection wells also, through surface structures also, but it can be recharged by the injection wells also. In hard rock terrain, you do not have such kind of much problems that you are having a much confined aquifer conditions. But in case of alluvial plains and other places you might have, or in sedimentary formations, you can have a confined aquifer conditions. So, these confined aquifers can also be recharged from injection wells, which we have already discussed. Under favorable conditions, fresh water can also store in saline water zones through well injections, and this is what it is done in coastal areas also, that we try to inject the fresh water through these injection wells, so that the saline water remain away from our groundwater aquifers. Now, for a spreading method of recharge, this is permeable zones that is done, and now if we want to recharge the augmented by subsurface capture of stream flows, and the example which I gave about Deprayag, the subsurface capture of stream flows, which is also called induced recharge, the nature of riverbed materials has to be evaluated first, and its water transmitting capabilities or characteristics should also be there. But generally you are having coarse grain unconsolidated material like the example which I shown. So, there will not be much issue if we go even for recharge, augment the water or take out the water or capture this stream flow in subsurface conditions. So, if we see overall in India what is happening about artificial recharge to groundwater in India, that the total annual groundwater recharge has been estimated as 432 billion cubic meters, and keeping an allocation of natural discharge, the annual extractable groundwater resource is 393 BCM. So, our recharge is this much, our extractable groundwater resource is 393. So, there is a gap. The total current annual groundwater extraction as in March, the data is available of March 2017 is 249 BCM. So, a lot of water is getting exploited or that. So, average stage of groundwater extraction for the country as a whole work out to be about 63%. So, that means only 37% of water resources left in subsurface conditions. If we do not recharge our groundwater regime or aquifers, we are going to have lot of problems. So, extractable groundwater already having problems. So, finally, we are coming to end of this discussion that extractable groundwater for various uses in different parts of the country is not uniform. Simple reason is the rainfall is not uniform, the geology is not uniform, or overall hydrogeological conditions on surface or subsurface are not uniform. And therefore, we should not expect that at every place we will have the same amount of water available for usage or whatever. So, out of total 6881 assessment units, that includes the block, mandals, talukas, firkas etc. in the country, 1186 units in various states, that is about 17%, have been categorized as overexploited. These areas should be the priority areas for artificial recharge. So, that this over is removed, over word is removed from there, and that is possible. What I am trying to say, whatever we have discussed about recharge of our aquifers is not impossible. Almost every place it is possible. Only thing is to find out the suitable sites, suitable locations and appropriate structures for groundwater recharge, indicating groundwater extraction exceeding the annually replenishable groundwater recharge. So, this is exceeding, and that is why the basically if I say in terms of budget, we are going in a deficit budget, and that is not good from even short term or long term point of view for a country. So, we should have a, if not a positive budget, surplus budget, but at least we should have a balanced budget, that whatever we are exploiting, we are replenishing by through our artificial recharge. So, in the areas, in these areas, the percentage of groundwater extraction is more than 100%, though theoretically looks more than 100%. So, how this more than 100%? Because at places people are going deeper and deeper and trying to exploit the water. So, it has at places it has reached about 100%, and that is again not good. So, finally, we are having like 330 units, about 5% are critical, where the stage of groundwater extraction is between 90 to 100%, and urgent measures are required in these areas to recharge our aquifers through whatever the means, either surface structures or subsurface through these injection wells and others. And if it is not done, this percent will keep increasing, these number of units will keep increasing, and the red areas in that map which I was showing will keep increasing, and that should not be the aim for the country. So, all efforts should be made, all possible efforts should be made, whatever is rain there, wherever it is there, the maximum effort should be to recharge, delay the surface runoff by some means, so that it recharge the groundwater regime. With this, I thank you very much.